this is Lowell Alleman, Distributed Databases, INFOST 410, Assessment Number 9. This presentation talks about distributed databases as defined by Christopher Date, published in 1987. This list is commonly referred to as Date's 12 Commandments of the Distributed Database. The global conceptual schema captures the idea of an overarching logical database view that transparently spans multiple backend databases. Throughout the Date Commandments, the idea of user transparency is repeatedly stressed. While researching the topic of distributed databases, I was only able to uncover two that align with Date's definition. These are historical databases, and they include SDD1, which is created by Computer Corporation of America between 1976 and 1978, and a database called RStar, which is an experimental distributed database system developed by IBM at the San Jose Research Laboratory at California. RStar was derived from the IBM System R, which was the first database to use SQL. Oracle jumped into the distributed game early on, but didn't work the same way. In 1993, Oracle added distributed support to Oracle 7, which was limited to distributed database processing and distributed querying. And even today, Oracle doesn't support relatively simple database constructs such as referential integrity across databases. In modern relation databases, the distributed feature set is essentially limited to database gateways. Under the covers, these gateways use a client-server connection. This means that connections are essentially one way. While it does not limit data from being transferred in either direction, it does mean that the originator, aka the client, can only initiate database operations to the remote database, the server. Database gateways in Microsoft SQL Server are called link servers. In Oracle, gateways are handled either by heterogeneous services or by, in the case of an Oracle to Oracle connection, they're handled by transparent gateway agents. Using synonyms can allow for transparent local access to remote entities like a table or a view. However, these must be created manually, and while they're transparent to the user, they're not transparent to the developer or the DBA. Beyond the scope of database gateways, no one has been talking about distributed databases since the mid-'80s. Date's commandment seemed to be based on the philosophical assumption that abstracting details away from the user or developer is preferred over forcing the user to be aware of and address the complexities of replication, locality, and consistency. Today's users are generally protected by an application layer, which shields them entirely from databases. Developers or report writers are the ones who are interacting with the database directly, and they pretty much have to know what's going on. Transparently proxying data between databases under the covers is going to lead to weird performance corner cases, and it leads to way more sophisticated code in the database, and generally speaking, the more complex the code, the more bugs that exist. But beyond my opinions, the market doesn't seem to agree with Date's hide it from the user approach, as I haven't been able to find any distributed databases that match Date's definition, again, since the 80s. The problems that Date is addressing in his list, they do represent a real problem. So my question I have is, why hasn't the problem been solved? And is it possible the problem has been solved in some other way? And I think that the answer to this question may lie in trends that we see in the market today. Overall, there seems to be a preference for application-centric solutions over database-centric solutions in the market today. ORM layers, for example, provide a layer of abstraction and can be used to connect to multiple databases if you're trying to form a horizontal partition. Another really interesting solution that's out there right now is Presto. Presto is an application layer SQL engine capable of talking to multiple backend databases. It was built by Facebook and then later released as open source. Presto handles online analytical processing workloads in the form of queries to Hadoop, but it's also quite capable of providing transparent connections to relational databases as well as other NoSQL databases. So let's take a closer look at Date's rules and see how they compare to the rest of the world today. Rule number 1, local site independence. The trend today is not towards independence. Most systems today have a very complex set of interdependence. The idea that every site maintains their own backup and security policies runs counter to the centralized management and authentication systems that we rely heavily on today. Today the focus is much more on high availability and disaster recovery. I think basically because we accept the risk that the dependency brings, and instead we kind of focus on how do we recover quickly. Rule number 2, central independence. Again, in today's organization, dependence is assumed. I think the central point Date is trying to get to here, though, is that we need to avoid single points of failure, and that on that point we completely agree. One solution to this problem is peer-to-peer infrastructure, and a few of the distributed databases that I've found actually do take this approach. Rule number 3, failure independence. The idea of fault tolerance continues to be a goal for modern systems. There is a more recent philosophical shift that's looking at the idea of designing for failure. And as the number of nodes grow, so does the likelihood of a failure. So modern designs sort of accept that as normal, and they plan for failure by building self-adaptive solutions. Rule number 4, location transparency. Today's distributed database support is primarily done by database gateways or linked servers. These connections are only one way, which is contrary to Date's original vision. As previously mentioned, a number of application solutions can help with this transparency problem. Fragmentation transparency. The original idea of hosting data closer to its source or destination sounds like a great idea on paper. However, because of increased network speed and bandwidth, reduced latency, lower hardware costs, and solid replication solutions, the value for this type of solution is diminished by the complexity that it introduces. Simply put, storage is relatively inexpensive now, and it's pretty cheap and easy to replicate the entire database. Date's horizontal partitioning has really given way to vertical partitioning, and that's primarily been done in the form of sharding. Replication transparency. The idea here is that duplicate copies of the data should be transparent to the user. This concept has not changed. Some of the NoSQL databases do trade on concurrency, so it is conceivable that the user could get a stale record, although technically that's still probably transparent to the user, but not what they wanted. Distributed query processing, rule number 7. The idea that queries extend beyond the single database is supported by relational databases today. This may not always be as transparent as we want, which we talked about earlier. Distributed transaction processing. Many of the top tier databases today do support transactions that occur across multiple environments. This is both possible in the database and from applications using XAOpen. Most of the time, this is transparent to the user unless something goes wrong. Now, what I found is that correctly writing multi-database applications that support distributed transactions tends to be a bit tedious and hard to get right. So before looking at rules 9 through 12, I should point out that each one of these rules in their full definition includes the word any, which basically means that none of them will ever be true. So let's take rule 9 for example. It says that databases must be able to run on any hardware. So if we take that literally, it would mean that an Oracle database should be able to run on my Raspberry Pi. That was like $35. Or if it doesn't, then it's not fully qualified as a distributed database. So last time I checked, Raspberry Pis are actually pretty powerful, especially compared to what we had in the 80s. But I don't think that Oracle releases their binaries for the ARM architecture. So for the sake of this discussion, we're going to drop any and assume that it means more than one. So, rule number 9, hardware independence. Almost everything runs on the Intel x86 64-bit hardware at this point in time. There certainly are other options out there. Many databases do support multiple platforms, and unfortunately some of these databases actually have their own proprietary hardware that is released by the company that releases the database, so that definitely is a restriction. I think overall this is a solid criteria. Uh, Number 10 is operating system independence. This is another really good thing to look at. I guess the only question I really have here is how we look at distribution or OSs like Linux and the different distributions. Like, are the different distributions considered different OSs or not? Um, and my thought on cross OS support has kind of been the idea of avoiding vendor lock-in, which is very different in the open source world anyways. Um, Number 11, network independence. I'm sure this seemed like a very good criteria when it was written, but today basically everything is TCP/IP, and very few general purpose applications or programs support any other network protocols. I don't really think that's a problem, basically because everybody supports it today. Perhaps maybe an equivalent today would be something like, don't make your database use multicast because that's not supported in some virtualized and cloud environments. Kind of going with the general theme there. So database independence rule number 12. Yeah, at the database level, this is just never going to happen. There's simply way too many databases out there to support them all. And again, remember that because of the word any in the definition, this would also include databases like SQLite, which have absolutely no intention of ever being network accessible, let alone participating in a distributed database environment. So, yeah, kind of lose there. But at the application level, things are much better. I would say that most databases are already there. Standards like ODBC and JDBC provide great value in this regard. So let's take a look at how some of the popular databases are handling distributed queries and transactions. As previously mentioned, both Oracle and SQL Server do support access to remote databases via gateways. This includes support for distributed transaction processing, DTP, and also using the XOpenXA standard, as well as multi-phase commits for data consistency. Heterogeneous database connectivity is handled using a shared protocol, which is either typically ODBC or OLEDB, and homogeneous database connectivity is used via native connection between databases, and that often results in improved compatibility or a wider feature set. So there still are several limitations to distributed queries, and I'm going to focus just on the ones that I've seen firsthand. I've run into data type conversion problems where the data is not formatted properly on the requester machine. Another challenge that I've found is the difficulty of tracking down user sessions across databases. So because the requests are all sent through a pooled connection between the two databases, and authentication is often handled by a single user account, it's very difficult on the receiver side to figure out where on the originator where the database connection actually came from, and specifically like who's doing what on the other side, because it all kind of gets masked as one user. So with that said, even in homogeneous solutions, beyond the things I've listed, things like database version, patch level, OS hardware, blah, 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 can all cause potential issues. That's a read the docs kind of moment. So what do the databases, distributed databases, look like today? My observation is that the word distributed is not used. I don't know if that's to avoid confusion with the historic 80s definition of distributed or not, but in any case, I have seen a frequent use of the words either grid or cluster, parallel, sometimes even cloud. They basically indicate kind of the same idea, at least in general, that we're looking at multiple independent nodes working together to form a cohesive logical unit. And the common traits among all these databases are, again, they're independent nodes working together, or interdependent, I guess you could say. And there's obviously a distribution and replication of data that's going on under the covers. So looking specifically at like massively parallel processing databases for a moment, which I kind of consider a subclassification of distributed databases. There are a number of shared characteristics there. The big three that I found were they have a shared nothing architecture, they have a column-based storage, and they also use a data sharding technique as far as getting the data spread out across different systems. Databases that would fall into this category would include Oracle Exadata, Vertica, Teradata, Greenplum, Amazon Redshift, Netezza. I don't know how to pronounce these, so let's go with it. There are a number of open source distributed databases on the market today. Redis provides a key value store with transaction support. They've also recently added clustering support. MongoDB is a document-oriented database that's capable of indexing fields within an adjacent document. Load balancing is handled by sharding, and height availability is achieved using replica sets. Solr is a search engine that provides both support for structured and textual search. Distributed searching is provided, again, through sharding, and high availability is attained through replication. Hadoop is kind of becoming the go-to choice for many companies when they're looking for a big data solution. And there's also a number of really interesting SQL layers built on top of Hadoop. And the ecosystem is really quite diverse, and every product has a very colorful name that I can't remember. So why would I want a heterogeneous environment? So first off, I think we should point out that the different types of databases offer very different capabilities. The traditional category of relational or SQL database is obviously one choice. Another choice is the non-relational camp, which, there's key value stores, document databases, search-oriented databases, some of the ones that we just kind of talked about. And so, it kind of becomes an interesting conversation. If your database is just basically if your application, I should say, is using your database as basically a simple data store, then you could be in luck and you might be able to choose whatever you want. Often this type of application is basically just using just tables and maybe views, but not much more. There's certainly no stored procedures or any other advanced database features. So you could really say they're very much database agnostic. Often I've seen simple like PHP web apps kind of fall into this category. Unfortunately, a lot of things don't fall into that category. So some vendors will actually go out and explicitly support multiple databases, and often that is because they're providing separate scripts for each database flavor. Sometimes they have to provide scripts for not just the flavor, but the flavor and version combination, depending on different changes from release to release. So basically for everything else, it ends up that the application mandates the database that you're going to use, unfortunately. That's been my experience. That's not necessarily always true. So, my conclusion basically is that heterogeneous environments are basically unavoidable in today's corporate environment. This really kind of comes down to, or it ends up becoming a management issue and a prioritization issue to say, is this a big deal or not? I mean, people often resist introducing a new database platform, but at some point you have to ask yourself, is this fight worth having? Do you have the staff to support the Nextdoor database or not? And what I found is that rarely when you go to a business person and say, hey, I got to convert PL SQL to T SQL, do they come back and go, hey, I think that should be your top priority. So that's sort of what it is. Now, there definitely are automated tools, and what I've found is that you still need developers to handle the complicated stuff. So, again, my conclusion is that heterogeneous is unavoidable. So, let's dig a little bit deeper on the topic of database gateways and talk about some specific use cases that I've kind of uncovered in my experience. I've set up a database gateway basically using a combination of synonyms, views, aliases to basically trick a SQL Server application into thinking that it was looking at a local table when really that table existed in an Oracle database in another system. I said trick in air quotes because the results were not transparent and it took several rounds of testing. So my first attempt, round one, I created a synonym in the SQL Server and basically just pointed it to the remote Oracle table. And it started to look like it worked, but then we got closer and found that it really wasn't. There was a data type discrepancy that was causing the joins to fail. Essentially, the Oracle side, one of the columns was a number field, and SQL Server thought it should be a varchar. And somehow in the process, like an extra decimal point got added to the mix, and like .0 was added to the end of all the values, which caused everything to fail at the join process. So round 2 was, let's make this just a little bit more complicated. We'll say, well, let's take the alias and swap it out for a view. So at that point, the SQL Server query would, the view actually contained the remote table as well as all the data type conversions. And it looked like this was working. And technically it did work, but it was basically unacceptably slow. I suspect what was happening under the covers is that the type conversion in the view was actually causing the remote query engine to not know precisely which value to look up because of the type conversion, which basically meant that instead of being an indexed lookup, it was now looking at a full table scan, which in the case of the scenario that we're talking about with a gateway means that that table scan became basically a table copy across the wire every time the query is run. So it was very, very slow. So the third and final attempt that we took was to create a custom SQL query, to make a custom SQL job that was scheduled to copy the data across from one database to the other. We tried a number of different approaches as far as how to make that work. We actually found that the fastest approach was to copy the entire table at the beginning of the process. The data went into a temporary table. We would add indexes to it, and then would basically compare that temp table against the active table, allowing us to basically do a local diff, which was definitely a lot faster than doing a remote cursor or looping over a remote cursor pointing to the remote table. And because all of that could be applied more quickly, we also found that actually reduced the number of locks in our very old version of SQL Server that we were dealing with. So I apologize in advance on this one. I had to cut out some details because this is being posted on YouTube. So let's talk about a case where I've used distributed databases from my past. So a small food manufacturer was looking to use RFID to track products around their various portions of the manufacturing facility and then use it for lot control. The challenge to this project was basically tracking the massive number of RFID tags in the environment, and there were network reliability issues and central database outages based on the way the database was used and the software that was on it. It required long weekend upgrade processes, which obviously becomes a problem for tracking RFID tags. You can't use the central database for that purpose if it's not available, obviously. So, and one additional complexity was the fact that there was long-term goals of providing off-site tracking as well. And during the design phase, we ran some numbers and came to the conclusion that we thought the RFID volume would be somewhere in the range of about 6,000 transactions per minute, for example, when a truck was being loaded, and that number was per doorway. And so basically the plan that we came up with was to use an Oracle database as kind of the master, which kind of already existed, and then create multiple application servers, and each application server would have its own MySQL database, and that's where all the RFID tagging would happen. So you'd have a database and an application server living on the same box. The idea was kind of like to make an appliance type of system. So if there was a failure, we could kind of like easily replace it, preferably without IT involvement so that we could sleep. So from a database content perspective, the central Oracle database, the master, was basically going to be housing the master record for the products, the locations, RFID keys, so on and so forth. And the MySQL database was basically going to have a cached copy of all of that data. And it would also house a queuing mechanism of some sort. The persistent queue was basically used for buffering the RFID scans that would eventually get pushed back up to the master for it to all be back in sync, but it would deal with any kind of offline kind of issues. So I do recognize this is not the typical distributed database model, and it doesn't even include distributed database querying across multiple databases directly, although an application certainly would have been doing that, would be doing that. And but I do think it represents the diversity in the distributed designs that exist today, and really how you can use multiple databases working together to accomplish many of the design goals that Date targeted, but aren't directly achievable in this sense. So I guess we should say it out loud. No database will ever meet all of Date's commandments. So knowing that, which one do I choose? There's a couple, I think, key questions to ask when looking at that. I think the first is kind of like, what kind of database functionality are you really looking for? I think another really big question is, where should my database live? What about my people? What about the staff? And are there trade-offs between the different options? So I think first and foremost, the most important step is to determine the nature of the use case. This will determine what kind of database is most relevant, which could be a traditional relational database or a key value store, document store, search, so on and so forth. Another big decision is where is the database going to live? And I think this depends a lot on, like, say, workload and your workload, your network latency, the tolerance that you have around your network latency, things like data governance, possibly like regulatory compliance, like, can only U.S. citizens touch my data? I mean, there's weird restrictions out there. Those things have to be factored in early on, I think. So, for example, say you needed either a temporary or a long-term elastic workload. In those kind of situations, and especially if you already have some things like hosted with, say, AWS or some other cloud provider, solutions like Redshift, DynamoDB, RDS, Aurora might really be a good and ideal fit for you. But if you have like high demands from a network perspective and you don't have reliable internet connectivity, those kind of things, like that's going to definitely rule out those types of options. But cloud is definitely becoming a bigger and bigger option for a lot of people these days. Another big factor to look at is skill set. It's very important to be strategic about the introduction of new technologies and to understand the mindset of the team involved. The more time in IT, the more value I see in looking at the human aspects of these types of processes. So what I've seen is, I would say for like most environments, like slowly introducing new technologies, new databases or whatever, gives developers time to get caught up and basically feel confident about their abilities and what they're doing. But it's interesting because on the other side, there are other teams that if you move too slowly, you actually start losing developers because they lose interest and they're ready to leave, and that's obviously not a good thing. And I think the last point I'm just going to throw in here is that it's important to, especially when looking at NoSQL databases, is to consider the trade-offs. There's often a trade-off between consistency, availability, and partitions, and there's it's something that really should be considered. There's a link in the references guide that talks a bit more about that. Eric Brewer, I think is his name. And it's really kind of a good way to kind of look at what it is that you actually need or don't need. I mean, the traditional data model with ACID support and all those types of things covers all of your bases. But often when you don't need that, you can find faster solutions in a NoSQL kind of way. Yeah, so I think that's enough about that. And here are some references. Thank you very much for your time.